Welcome to the lecture on the water planet. This is the second time through this. Why? The first time, the lecture went 15 minutes and 4 seconds. YouTube accepts only 15 minutes. Oops. Got a little background music to make it peaceful, so put on your headphones and enjoy. The beginnings of oceanography. Well, let's look at the word first. Ocean, graphy. To graph means to write. Ocean means, well, the water. It comes from the Greek okeanos, O-K-E-A-N-O-S, graphos, G-R-A-P-H-O, grapho. Ocean, okay, okeanos and graphos, oceanography, like, well, this. 70% of Earth's surface is water. And if we could shave off or wear down or grind down the continents and put them under the water, the continents would be covered up, or the land would be covered up by a long dive under the water. I won't tell you how much because that is one of the questions from your study sheet. Modern oceanography. We've got all kinds of instruments to investigate the ocean, and your book covers those well, so I'm not going to talk about them. I will, however, talk about properties of water and the density. Water is not very compressible. You put water into like a plastic bottle and try and squeeze it, it doesn't work. Do that with air. Air is very compressible. However, you can change the density of water. How? You just add materials that go between the water particles, like salts, or you cool them down, the water particles down. What I mean? Remember back to the motion of particles in a liquid. Liquid particles zoom all over the place. The hotter we make them, the faster they zoom, and the colder we make them, the slower they move around, until when they get to the freezing point, they simply stop and vibrate back and forth in place. This is significant because when that happens, ice actually takes up more space than does the water from which it came. Sorry, yeah, that's right. So the ice is less dense. That means when water becomes cold, the ice rises. What would it be like if this didn't happen? Looking at this cold lake, if this were just the opposite, if the ice became more dense, it would freeze on the surface, go down and sink. More water on the surface would freeze and go down and sink. So lakes would freeze from the bottom to the top and all the fish would die, or they would have evolved to tolerate that. As it is right now, the ice insulates the top, which is a little bit weird, I know, and the liquid water underneath stays, well, liquid. Now, why does this happen? Why does water go from a rather dense liquid to a less dense solid? It's because the water molecule is what we call polar. One oxygen, two hydrogens. The oxygen steals the electrons from each of the hydrogens, H2O, and the oxygen becomes negatively charged. The hydrogen end becomes positively charged. I like to think of it this way. If you're in a really crowded hallway at school, you don't mind walking through people as long as you're walking. But imagine if everybody just had to stop and stay that tight. Not that good of a feeling if you don't like crowds. As long as water's in liquid form, these particles can move past each other okay. But when they solidify and vibrate in place, these particles scoot apart from each other, and ice takes up more space, becoming less dense. Because water is polar, it dissolves other polar things and it dissolves non-polar things. What does it dissolve really well? Well, any of the salts that wash into the ocean from the land. In fact, 3.5% of the water is salts. Not just sodium chloride, but magnesium chloride, magnesium sulfate, carbonates, things like that. For some reason, oceanographers don't like to deal in percents, and they will talk about 35 parts per thousand. Weird, I know. Maybe it keeps them in a job. This is the graphic from your textbook. It's okay. This is a better one, and it shows you, both in pie form and in bar graph form, what the most common ions are. Chloride, sodium, making up sodium chloride. Sulfate, sodium sulfate, gypsum. Magnesium, carbonate, where's the carbonates? There you go. Calcium, potassium, bicarbonate, bromide, borate, strontium, fluoride. And by that time, we're getting down to very little stuff. Kind of cool. Now, the ocean isn't the same salinity all over. Where you have a lot of rain going on, like at the equator where the air rises and then drops back down, creating fresh water, you end up with lower salinity water. When you get up to the poles, in particular by the Antarctic, notice that it's very saline. Why? Is there a lot of salt washing in here? No, in fact, it's kind of the opposite. Any of the water that makes its way down here freezes into ice, and it's not the salt that freezes, just the water. What's left behind? The salt. So that salt stays behind in this water, which makes it very saline, which also makes it very dense, which tends to make it sink. Let's take a look at North America, South America, and Panama right here. The trade winds blow the waters this direction, but the waters blowing up this direction tend to evaporate, and as they evaporate, they leave behind the salts. So you end up with 3.7% or 37 parts per thousand salinity here, and on this side down to 32 parts per thousand. I know this is weird, but going from 32 parts per thousand to 37 parts per thousand, that's a change of 5 out of 32, so that's about a 16% difference right there. That's a really big difference, and it affects the sea life, the coral, everything that's in that area. And yes, coral is sea life. Notice the temperatures are slightly different too. 25 degrees Celsius all over here, just barely 25 right along here. Again, because the evaporation and condensation and precipitation. Now this is what goes on near Antarctica. The water freezing here stays behind, the salt water sinks and creates these currents, these circumpolar deep water currents that may take between 1 and 2,000 years to create an entire cycle. Now some of this water that sinks has a lot of nutrients with it, and believe it or not, dissolved oxygen, and that oxygen stays down here for those centuries. So when this water comes back up to the surface, it carries with it some oxygen and a lot of nutrients, and fish feeding off the coast of, let's say, South America, for example, love this when it happens because they will go crazy. You get these algae blooms, and the fish eat the algae, the medium fish eat the small fish, the big fish eat the little fish, and then people come along and eat everything else, and then leave our plastic behind. Because that's what we do. Here's another nice example of what is called thermohaline, like halite, salt, circulation. Now, let's talk about temperatures. The mixed layer of the ocean, 50 to about 300 meters deep. I know it doesn't seem like that to you. If you're ever in a swimming pool, you notice the top water is really warm and the bottom water tends to be cold down by your feet. In the ocean, that's true, but for about the first 50 to 300 meters, things are fairly mixed, and this area is oxygenated. So that's where most of the life in the ocean is. After that, we go through a thermocline. Thermal, heat, cline, change. Change in heat, and the temperature drops quickly. And after that, you're in the bathyal zone or the deep water. A lot less life, a lot less oxygen. Here's another example of the variations in temperature. The dark stuff is the land. The red, the yellow, the green, and the blue is the ocean. Here's Miami, Florida. Here's Cuba. Here's New York. Here is hot water flowing out of the Gulf. Because it's hot, it's less dense, and it stays on the surface. This is why New York is warmer than it should be. It's also why England and Iceland can be warmer than they should be, because water's trending up north and then east tend to warm the northern parts of Europe. One concern is, as the ice up here melts, that fresh water that's melting, even though it's cold, will stay on the surface, and it may divert this water, making it go further south and cooling off northern Europe, which could be good for them. Here's some major temperature currents in the ocean. We'll get into more currents next chapter. But something to notice. Take a look at the east coast of the United States. We have warm water coming up from the Gulf Stream, going all the way up to Norway. Yeah, you betcha. The same thing happens down here on South America. Warm waters coming across here heat up the east coast of Brazil. But take a look at the west coast. Due to the circulation patterns, counterclockwise in the southern hemisphere, clockwise in the northern hemisphere, the west coasts tend to have cold water. Think about this. You go to California, you think you're going to go swim off Los Angeles, you head into the water, brr, it's cold. You go over to North Carolina, even though it's further north, the water is warm, even in September at midnight. I know, I've been there. It's fantastic. Apparently the sharks are there too, and I didn't know that at the time. But any East Coast tends to be warmer than the same place, latitude-wise, as the West Coast. Take a look at Australia, right? You're warm over here, cold over here. Pacific, cold here, warm over here. The British have known about this for a long time. They diagrammed this thing called the Gulf Stream, and then they used it to get across the northern way, and then to head back south the southern way. Let's talk about the ocean floor. We've got about 3 minutes and we can sneak this in. We could send your buddy with a snorkel or a really big bubble over his head down to the bottom of the ocean, pick up some stuff, and then come back and he could tell you how deep it is. But that's really slow and you'd get tired arms. A better way is to do sonar. Now believe it or not, you do sonar, at least you probably did as a kid. Have you ever closed your eyes and walked around your house, either at night or with closed eyes, and made sounds listening to the echoes from the walls? Believe it or not, we can do this too, we just don't pay attention to it. If the lights ever go out in a room, try this, just not a crowded room. But you can tell when you're close to a wall. We do the same thing, we essentially just echo things off the bottom, measure the time return, and then create an image out of it. We also use satellites which now can penetrate the water. Pretty cool. We also drop drill cores down and get the history of the ocean by looking at layers of sediments. But again, that's covered really well in your book. I don't need to talk about it. This was a split image in your book. I've assembled it into one image here. There's a lot of stuff under there. The world's longest mountain range. The mid-ocean ridge, over 40,000 kilometers long. Way higher than anything on Earth. We've got mountains, we've got trenches right across here. It's really cool. But most of the ocean is incredibly flat. Let's look at what we call the continental margins. Here's the continent. It's made primarily of granite, about 3.3 grams per cubic centimeter. It's less dense than the ocean, which is about 3.5 grams per cubic centimeter, which is why the continents are the continents. They're light, they're floating. They're never going to sink down unless you have something really big sit on top of them. Hopefully not a big meteorite or something like that. Here's where the continent extends into the ocean. All the sediments on top of it, terrigenous sediments coming from the river, into the delta, down the submarine canyon, and making an underwater type of alluvial fan, which is a little strange. All this is part of the continental shelf. It really is part of the continent. Where we drop off the shelf, we have the slope, and then the rise. Shelf, slope, and then the rise. Then finally you're out to the official part of the ocean. Is this really the case? This is just some silly artist drawing. No, it really is the case. Here's the east coast of the United States, where the shelf is incredibly wide. You're looking at more than 200 miles wide in some cases, which means the real rock of the earth, the continents, extends way out here. It's just that the oceans have risen far enough since the melting of the glaciers to cover that up. Let's zoom in on that little canyon right there. There it is. The continental shelf, continental slope, and then the rise, and we've got a canyon underneath there, which is kind of cool. These canyons can form two ways. Either you have denser waters etching out this really soft sediment, or this is the remnants of a canyon from when all this water was on land when it was a colder climate. I'm going to pause there, hopefully, and we'll pick it up on the other side.